Okay, in this video we're going to consider the problem of filtering the ripple out of the output of our full wave rectifier. And when we're trying to create a DC signal, any sinusoidal components that are added to it are referred to as ripple. So we'd like to try to attenuate those sinusoidal components. Again, attenuation being the opposite of amplification. So how can we analyze this? We can analyze this using our knowledge of frequency response. So suppose that our output of our rectifier is given by a Fourier series, such as the ones we showed last time. So it's the sum from n equals minus infinity to infinity of c sub n e to the j 2 pi n over capital T little t, or it could be written in terms of real valued sinusoids. And suppose that we now wish to attenuate the sinusoidal components to get rid of the ripple, but ideally not the DC component. Suppose that in order to do so, we pass the signal through an LTI system with a given transfer function h of s. Then we know that the output well, we can get the output by simply finding the response to each of the terms in the Fourier series, and by linearity simply adding them up. Let me just, yeah. So all we have to do is find the frequency response of the system, namely the transfer function, evaluated at j omega, where omega is the angular frequency of the sinusoid in question. So if we find all these responses to the respective complex sinusoids, by linearity, their sum will be the overall response of our filter to the output of the rectifier. And as we know, it's convenient to break up the frequency response into magnitude and phase. So we can rewrite this as Cn times the magnitude of the frequency response times e to the j times omega t plus the angle of the frequency response. Okay. So if you like, we can easily find a series that represents the output of the filter. But suppose now that we wish to design a filter. Okay, so we need to decide what we want this magnitude to look like, for instance. Here we're going to be concerned primarily with the magnitude. We want to decrease the magnitude of the sinusoidal components, and we don't want to decrease the magnitude of the DC component. And we'll be able to quantify how well we've done this by, again, applying Parseval's theorem. So in particular, we wish to pass the DC component but block or attenuate the sinusoidal components of the rectifier output, but in particular, the most troublesome one is the largest one, and the lowest frequency one is at twice the input of the twice the frequency of the input signal. So that'll be 2 pi 2 over t, 4 pi over t, or 2 omega, where omega was the angular frequency of the input signal. Okay, so suppose then that we wish to decrease the power in the component at this frequency, this lowest frequency sinusoidal component, by a factor of, say, let's see, what's the power in our DC component? The DC component was 2a over pi, so its power is 4 over pi squared a squared. So, roughly 4/9 or so, roughly say 1/2 a squared. The component at 2 omega radians per second, according to the Fourier series, has an amplitude of 4 over pi a times 1/3. So its power, because this is a sinusoidal component, is going to be 1/2 the square of this quantity. So what's that going to give us? 1/2 16 over pi squared a squared times 1/9, or in other words, 8/9 a squared over pi squared. So considerably less, less than a quarter of the power in the DC component. But suppose we want to decrease it more. Suppose we want it to be only about 1% of the power in the DC component. In that case, we need to reduce it by a factor of 25. It's already about a quarter. Or in decibels, if we wanted to put it into decibels, we would take 10 times its log. We wouldn't use 20 times its log because here we're talking about power, which is already proportional to the square of the signal. So 10 log 25 decibels works out to about 14 decibels. So let's make it a round number and let's go for 20 decibels of attenuation. Now 20 decibels, that's a familiar figure. When we were drawing Bode plots, we often ended up with slopes of minus 20 decibels per decade. In particular, that's what we had for a simple first order filter. So if we design such a first order filter and we have a high frequency asymptote with a slope of 20 decibels per decade, what we often call a high frequency roll off of 20 decibels per decade, then this essentially just means that if this component that we're trying to attenuate at twice the angular frequency of the input signal is, say, 1 decade above the corner frequency of the Bode plot of our first order filter, then it's going to be attenuated by 20 decibels relative to the low frequency asymptote. We'll go through all of that. So let's suppose we're just going to use a simple first order filter. So suppose we've got So in order to get our 20 decibels of attenuation, we want the frequency 2 omega to be 1 decade above the corner frequency of the filter. And the corner frequency for a first order system is the reciprocal of the time constant. So let's try then designing our filter so that its corner frequency is 1 decade below this frequency 2 omega of the lowest frequency sinusoidal component. So in other words, we want this to be 1 over tau. And that means that we want the time constant tau, which works out to be the product of R and C for the circuit, to be 5 over omega, where this omega again is a particular omega. It's the angular frequency of our input sinusoid. Okay, in that case, this circuit has a DC gain of 1. To see that, just suppose that you have a constant voltage at the input and a constant voltage at the output. Then this capacitor is going to get charged up, and after that it will effectively behave like an open circuit. That's the intuition behind the circuit design. But its DC gain is going to be 1. So the DC component of the filter output will be the DC component 2a over pi of the rectifier output times the DC gain of the filter, h of 0. But again, that DC gain is going to be 1. So we'll get 2a over pi again as the DC component of our signal once it's gone through the filter. But the high frequency roll-off of our first order filter will decrease the amplitude of the sinusoidal component at 2 omega. It's going to be 4a over pi times 1/3 its original amplitude times the magnitude of the frequency response So we see from here that omega tau is going to be 5. So 2 omega tau is going to be 10. So the modulus of this lowest frequency sinusoidal component is going to be approximately decreased by a factor of 10.5, which gives us roughly 0.04 times the amplitude of the original AC voltage. So if we compare the powers, the power of the DC component is as it was before. The DC component is 2a over pi, so the power in that DC component is 4a squared over pi squared. While the power in the sinusoidal component at 2 omega is going to be 1/2 the square of this amplitude. So it will be 1/2. The amplitude was about 4 times 10 to the minus 2a, so its square will be about 16 times 10 to the minus 4a squared. In other words, 8 times 10 to the minus 4a squared. So even with this simple first order filter, we do get a very big difference between the power in the DC component and the power in the most significant AC component. And we've used a bit of our knowledge of frequency response and Bode plots in order to design this simple filter. So we could use a fancier filter if we wanted better performance. You would normally add an additional circuit called a voltage regulator after this anyway. But this describes some of the key steps in building a DC power supply. So again, this is the sort of power supply that you use to charge your phone or your laptop. And we use some of the ideas we've developed in this course in order to do it, specifically the Fourier series and frequency response. So let's wrap up this video here.